Hi there. Well, we're going to start our last sections that we'll be covering this semester, and this section is going to be 10.8, which we're going to put in with chapter 11 because they pretty much go well together. Well, what we're going to start looking at are imaginary numbers, and the imaginary numbers allow us to solve equations that we haven't been able to solve before. And imaginary numbers are also used in electronics. Anytime you have waves, whether it's an alternating current, sound waves, anything that repeats, the imaginary numbers have applications there. But so we're going to be talking about these imaginary numbers. Now, before we had real numbers, okay, what we've been dealing with are the real numbers so far. Oops, just a second. Okay, so we've had real numbers. And again, this is just kind of an introduction. The real numbers included any number that, we could think about, fractions, negatives, zero, radicals, okay? All of these were considered real numbers. Now, our real numbers, these are the only ones we've been working with, the only ones we've been allowed to use. These were divided into rational, and we'll talk about that here in just a second more. Rational numbers or irrational numbers. Irrational numbers. Okay, so now what we're going to do is we're going to take our real numbers. We're still going to be working in the real number system, but we're going to expand it so that we're able to solve different types of problems that we haven't been able to before. As an example, if I were to give you x squared plus 4 equals 0, and we were asked, okay, what can you square, add to 4, and get 0? Well, there was a mathematician named Euler. It's pronounced Euler, and he kind of thought, well, let's imagine. Well, because of those words, we have imaginary numbers. And it allows us, we're going to introduce a new number here that allows us to solve this here. And again, also it has applications in electronics. So what we're going to do is we're going to talk about this special number that Euler has that allows us to solve this equation to come up with an answer that we weren't able to before. So let's go ahead and let's look at our number that we have. Let's go to the notes now. So we're expanding our real number system to include something that allows us to solve things like the x squared plus 4. It allows us to work with wave theories, with these with electronics, adding alternating currents that are out of phase, things like that. So let's talk about our imaginary number. Now, the number I is going to be our imaginary number. And its definition is I is equal to the square root of a -1. So I squared is equal to a -1. So we have our definition of our imaginary number. I squared equals a -1. Now what that allows us to do, knowing this, and we're going to go through a bunch of examples so it kind of all fits, is it allows us to find the square root of a negative number. Okay, whereas before we weren't able to do that. If you were given this in the last chapter, you would say your answer is not a real number. But now we're going to be able to solve it. A -1, okay, an I squared can replace a -1. So in other words, this is I squared times 7. Okay. -1 times 7 is a -7. This negative, this right here, if you have 2 of something, it comes out. And the 7 stays. So the square root of a -7 is now I square roots of 7 using imaginary numbers, the imaginary number of I. Okay, so I is equal to the square root of a -1. So when you have a negative in a radical, okay, you can write it as an I. Okay, let's look at another one. If I have the square root of a -16, if we're allowed to use imaginary numbers rather than being limited to the real number system, this would be equal to square root of 16 is 4. The square root of this negative is I. Okay. Because this could have been written as I squared. I squared is a -1. So instead of this negative, I'm going to put I squared times 16. And this right here, you have two I's, they come out. The 16 has two 4's, and it comes out. So whenever you've got that negative inside, and again, if you notice, these are square roots. These aren't cube roots or fifth roots. So you're only going to need that I if you have an even index. When you have an even index and you have a negative inside, you're now able to, with this imaginary number, have it come out as an I. All right, let's look at C. I've got a -12. Well, we're going to have 4 times 3. We'll reduce that. Okay. So here, the 2's will come out. The negative will come out as an I, but the 3 stays. And so reducing this using an imaginary number, you'll have 2I square roots of 3, rather than no answer because we're in the real number system. So this would be your answer using imaginary numbers. Let's do another one. And again, this is dealing with square roots. We have an even index with all of these. Let's look at this one. Now we have a negative on the outside. If you have a negative on the outside, it'll stay there. So we have this negative. This will come out. Okay, the square root of a -1 is I. Because we have an I squared, if you have 2 of something, it comes out. So we'll have a -I. Okay, that takes care of that. Now the 13 can't be reduced. There's not 2 of anything. So it stays. So your answer is a -I, and then the square root of 13 stays. And there's your answer. Okay. All right. Let's look at another one. We have a -50. So we know the negative will come out as an I. All right. But what about the 50? Can it be reduced? Let's go 10 times 5. 2 times 5. Okay, we have 2 of those. They'll come out. The negative will come out as an I, and the 2 will remain. So we'll end up with 5I. The 5, the negative comes out as an I, because again, it's an I squared. If you have 2 of something, it comes out. Square root of 2. It stays inside. Okay, so we have 5I square roots of 2. Again, let's try this next one, F. The negative outside. So, don't be tempted to say, okay, a negative and a negative is a positive, because that's not how it works. You can't just bring that negative in, and you can't just bring the negative out. All right. This negative has to come out as an I. So you either look at it as the fact that the square root of a -1 is I. That's a -1. Or a -1 is I squared. So if you have 2 of them, it comes out. Or the fact that you can just substitute, if you have a -1, it becomes an I. Either idea, okay, whatever makes most sense to you. So this right here is the same thing as I squared times 300. Okay. So the I squared comes out. Now again, that negative that we started with outside stays. The 300 is 100 times 3, 10 times 10. So I'm going to move my negative I over or down. So we have our negative, we have our I. This 10 will come out. I'll put it in front of the I, and the square root of 3 has to stay. So I'll rewrite it. It's a little messy. So there's really, it's not really too complicated. Just remember that when you have a negative inside of a radical now, we are able to deal with that negative inside that radical using what we call an imaginary number. And when you do have that negative inside of an even radical, in this case, inside of the square root, you have an even index of 2, it will come out, all right, as an I. If this is a 2, now remember we were looking for 2, okay? I don't know if we're gonna look at fourth roots or not. We'll just deal with the square roots for right now. Just remember it comes out of a square root as an I. Okay, so let's talk about imaginary numbers and putting them together with our real numbers. When you take an imaginary number and you put it together with real numbers, so we still have our real numbers, we're just adding something in. We're adding imaginary numbers in that allow us to deal with something like this, which in turn allows us to solve this equation right here, which we'll talk about after a while. So it allows us to find an answer. What can you square and add 4 to it and get 0? And it all starts with this right here, dealing with a negative inside of a square root, okay, which we're allowed to do now. We come up with an I squared. So the imaginary numbers will come in here in both of these cases here. Now, let's take our real, okay, let's mix it with our imaginary. And when you do, we have what's called a complex number. So a complex number is a real number, it's an imaginary number, and it's a combination of both. So we have expanded our real number system, the numbers that we were allowed to work with before we were here. This is all we had. And in that case, real numbers, here you have a real part and you have an imaginary part. So we'll kind of back up here. Complex numbers, okay, here, this A represents the real that we've always had. This represents our new number that we have, BI. Now, up to now, the B has been 0. All we've had is the real part. That's what this is saying here. And our complex number, which is a combination of the real with the imaginary, the B part, the imaginary part, was 0. And over here, okay, you can have what's called a pure imaginary number. So here, the imaginary part is gone. Imaginary numbers, what we were dealing with just right before, the A is gone. All right, and so you do have this imaginary part. So this is our new section where you've got, well, the pure, I guess, the pure imaginaries are down here. But you have an imaginary part and a real part. Okay, so let's look at these complex numbers. And let's say, okay, are they real numbers only? Do they include imaginary numbers, and kind of break them down? So let's talk about our 2 plus 2i. Now we know that it has an imaginary part, so 2 plus 2i would go into this box. Okay, it would be considered an imaginary number. Okay. All right, now let's take this further. Let's take each number. 2 plus 2i. Is it a pure imaginary number? If it is, then this part is gone. Pure imaginaries don't have that real added or subtracted here. So with a pure imaginary, the A is 0. This is not a pure imaginary. This is a complex number, complex number that includes both the real and the imaginary. So this one belongs here. It's a complex number, a complex imaginary number. All right, let's talk about 0. Where would we put 0 at? Well, 0, okay, 0, this number does not have an imaginary part with it. So we're going to put 0 over here, okay, as a real number. It doesn't have an I. Is it rational or irrational? Well, we know irrationals are things like pi, square root of 3, anything that's not a fraction, anything that's not a decimal that repeats or a decimal that stops. These are fractions that keep going without repeating. So 0 would be a rational number. Okay. All right, let's go to the next one, negative 18. Negative 18 does not have an imaginary part with it. It doesn't have that I, so it would be considered a real number, and it's not irrational. Okay, so it would go here. What about this one right here? 2/3 minus 7/5 I. You've got the I, so we automatically know that we're dealing with an imaginary numbers. Now, is it pure imaginary? Pure imaginary means there's no real part to it. And again, that real part is this right here. So this right here would be considered a complex imaginary number because it's got the real part and it has the imaginary part to it. So we would put it over there. All right, let's look at pi. Let's look at our next number, pi. There's no I, so it doesn't go here. Pi is a real number, just a real number. And pi is irrational. It cannot be expressed as a fraction. Okay. So it's a decimal. If it were a decimal, it would not repeat. Okay, it keeps on going. Let's look at our negative 3i. Negative 3i, it has our imaginary part with it. So it would be considered an imaginary number. But is it a complex imaginary number? Complex meaning it has a real part and an imaginary part. Or is it a pure imaginary number? And in this case, negative 3i is a pure imaginary number because it doesn't have the a. It's just a pure imaginary number. Okay, let's do a negative, let's do 2/3 I is our next one. 2/3 I goes here. All right, it's an imaginary number, but is it a complex imaginary number, meaning it has a real part and an imaginary part, or is it just a pure imaginary number with no real part added on? And in this case, it's a pure imaginary number. It's just 2/3 I. Let's look at 2/3, our next one. 2/3 does not have an I, just 2/3, so it's what we've always worked with. It's a real number, no imaginary part to it. And it is rational because it can be expressed as a fraction. It is a fraction. Okay. Square root of 2, no I. Square root of 2 is a real number. It's just a real number. And it's irrational. Any of your radicals that cannot be reduced, square root of 2, square root of 3, square root of 5, square root of 7, square root of 11, square root of 13. All of these would be non-repeating, non-ending decimals. So this is considered irrational. All right, let's do maybe, okay, we can go ahead and finish these. 5 minus 4i. You've got an I, so it would be considered an imaginary number. So it's going to go in this box right here. It has, 5 minus 4i has an a, which is considered, the 5 is called our real part. The 4i is called the imaginary part. So when you have a real and you have an imaginary, you have a real and an imaginary, a real and an imaginary, and they'll be separated by either a plus sign or a subtraction sign, always. So the real and the imaginary will be separated by a plus or minus sign in your complex numbers. In this case, it would go here because there's my real, 5, and subtract my imaginary part. So that would be considered a complex number, a real part with an imaginary part. And you can graph these, which we're not going to get into as far as on a coordinate system, but you can plot the real part with the imaginary part. Okay, let's look at 5. 5, no imaginary, it's considered just a real number. And it's also rational. 5/1. It stops. It can be, written as a fraction, 5/1. Okay, the square root of a -7. Well, up to this point, we would have said that's not possible. But now we can't say that. The square root of a -7, we now know, is I square roots of 7. Those two mean the same thing. We're using imaginary number. The imaginary number meaning that I squared equals a -1. We're able to square something and come up with a negative. So simplifying this, substituting in I squared here, the I comes out. I square roots of 7 is imaginary. So it's going to come over here into this box. It does not have the real part to it. So it's a pure imaginary number. Okay. And 9.1, last one. 9.1, there's no I, so we have, it's just a real number, and it's a rational number because it's a decimal that stops. Rationals would be stop or repeat, would go in this box. All righty. Well, I'm hoping that kind of makes sense. And again, we'll just kind of be working with these. We're just introducing this new number system that, kind of opens up the ability to solve problems we've never been able to solve before using this, our imaginary number I. It's just kind of unfortunate that they chose the word imaginary. Kind of bothers people. Okay, so what we're going to do is we're going to learn how to work with these complex numbers. How do you add a complex number, subtract complex numbers? How do you multiply them together? How do you divide? So that's kind of what we're going to be concentrating on right now. And then when we start chapter 11, we'll start solving problems, solving the equations we weren't able to do before. And we'll learn how to use the imaginary number to solve those. But let's go ahead and we're going to add them. And again, don't make this any more difficult than it is. It doesn't mean to be. But when you want to add these two, I've got two complex numbers. They both have a real part and they both have an imaginary part. Now, when you add these, you add the real parts together and then you add the imaginary parts together. So it really is similar to if that were a variable, x. Okay, you would add the 8 and the 3 because they don't have that. So 8 and 3 give you 11. And then you add your imaginary parts, or those with the I. And there's your answer. So your answer is the complex number 11 plus 8i, where you've got the real part is 11 and the complex part is 8i. Okay, let's look at B. Now we're subtracting, and so you have to remember that when you have a negative outside of your parentheses, it will change the sign on what's inside. Those rules still apply. So we have 4 plus 5i. Now this right here, this is going to become a minus 6. Right inside it's a positive. So this is going to change it to minus 6 plus 3i. So again, it changes those, kind of what we've done since chapter, I don't know, 3 maybe, 4, maybe 3. It was 3. So now then when we combine these, the reals are 4 and minus 6. So the real part of our answer is a minus 2. The imaginary part is a plus 8i. So we have a minus 2 plus 8i is your answer. Okay, the real part and the imaginary part form a complex number. It's just kind of neat that we have this all new number system to work with and to solve. It's kind of cool. All right. Let's do this one right here just to kind of make sure it's, you know, those subtractions outside of parentheses kind of give people fits. So here, okay, inside it's a -7. So because of this negative out here, this is going to become +7, and the positive I will become a -I. So that subtraction changes this to a plus and change that to a minus. So now when we combine our real part, 7 and a -2, we get 5. And then we combine our imaginary parts of our complex numbers. 6i and a -1i is 5i, positive 5i. So we have 5 plus 5i as being our complex number. And maybe there'll be times when you add these together that you only end up with a real because the imaginaries drop out, or you may end up with just a pure imaginary because the reals add up to 0. You know, that can happen as well. But in all three cases, when we added our two complex numbers, we ended up with a complex number, meaning it's got the real and the imaginary as well. Okay, let's look at our last one here. Again, testing that negative outside of the parentheses. We have a -4i. The 12 will become a -12. And the 14 will become a -14i. Okay, wow. So the -12 has to stay by itself. It's the only real part. There aren't any other real parts in order to combine it with. But these two imaginaries, you can combine a -4 and a -14, subtract 14 there, and you come up with a -18i. You know, kind of notice the order. We like this. We like this order. Notice I'm putting the real part first, and I'm putting the imaginary part second in our complex number. And that's just kind of convention that we like it. We like it to look like our A plus BI, where here's your real and here's your imaginary. So just kind of get used to putting the real first, followed by the imaginary. We just like it that way. Okay. Let's move on. So, you know, I'm hoping that adding and subtracting isn't really too bad. So that we can go on to multiplying. Yay, multiplying. All right. First off, the index here, the indices here are the same. They're both a square root. And notice on this, in this whole section, I'm dealing with square roots. Okay, these are square roots. We're looking for 2 of something. Now, if I have these right here, you might be tempted to say, wow, in the last chapter, we just multiplied them together. A -5 times a -7 is a positive 35. They disappear. The negatives disappear. But you cannot do that. So unfortunately, this is kind of like a different type of a rule in that when you have these, you need to simplify these first, getting rid of the I, bringing it out before you multiply. So again, do not multiply roots with negatives still inside them. So what we're saying here is that you need to take the negatives out before you multiply. Well, how do you take a negative out of a radical? Well, that was kind of what we talked about on that first page. And that this right here is I square roots of 5. So the negative comes out as an I because a -1 is I squared, and I squared comes out as an I. Okay, so the square root of this -1 is I times this negative will come out as an I. Okay. So those negatives inside the square roots come out as an I. Now that you've simplified it, obviously the 5 can't be simplified and the 7 can't be simplified. So now that you do that, you can multiply what's inside together. So this becomes, well, what's outside is I squared. You multiply what's outside, you get I squared, adding exponents. So these i's, I mean, they follow the rules of exponents. You know, if you have a power to a power, you multiply. When you're multiplying common bases, you add exponents. So, you know, they really do have the same properties when you're adding or multiplying that we did with just regular bases. But what's I squared equal to? Well, we know that I squared is a -1 because we use the I squared as a -1 to pull it out. I squared, this is an I squared, it comes out as an I, okay? And so here, we're gonna substitute it back. So this, I guess I can put it down here, is equal to a negative. I squared is a -1. So we pulled these out, then we multiplied them, and they follow the same rules as our common bases. You add exponents. But then we have to remember this imaginary number. By definition, I squared is equal to a -1. So rather than writing a squared, I'm going to write a -1. You don't have to put the 1 in, but if you do, it's not wrong. But you don't. We normally do that. So here. Wow, and that's fun. Okay, you guys, you'll be fine. You're going to get this. Okay, so let's just keep going through some examples, and eventually maybe it'll start to click. And if not, you just need to let me know, and we'll meet on Zoom and go through a few more examples. But again, we need to simplify these before we multiply them together. So I'm going to take out an I from both of these. So this one right here, the I comes out, but also 4 has 2 2's in it. So the square root of 4 is 2. So this is 2I. Okay. I might even just I'm going to erase it and put it underneath a little bit closer. So this right here is 2I. All right, the negative came out as the I and the 4 came out as the 2 and nothing was left. So then we're going to go to this one. The negative comes out as an I because this negative represents I squared. And when you have, because a -1, this is a -1 times 25. They mean the same thing. This -1 is I squared. And if you have 2 of something, it comes out as 1. 25 has 2 5s. So you come up with 5I. The I coming from the negative inside of our square root, and the 25, the square root of 25 is 5. So once we've simplified them, which we've done, we're going to multiply. So multiplying the 5 and the 2, you get 10. I times I is I squared. So they follow those same rules as adding exponents. But we do know that I squared is a -1. 10 times a -1 is a -10. So there's our answer. Okay, well, let's look at another one. Here we have a -3 times a times 8I. Okay, so here again we're not going to have to reduce. Okay, we're to the point where we're just going to multiply them together. -3 times 8 is a -24. I squared, because I times I is I squared. I squared is a -1. So a -24 times a -1 is a +24. Because remember, this means a -24 times I squared. When they're next to each other, you multiply. So it's a -24 times, because I squared is a -1, -24 times a -1 is +24. So there's your answer, +24. Negative times a negative is a positive. All righty, let's see what we can do with the next one. Here, again, multiplying this through, simplifying it. Let me kind of adjust that a little bit. we'll use the distributive property. We're going to take this times here and this times this right here. So negative 4i times 3 is a negative 12i. Okay, I just multiplied the negative 4i times 3. Now I'm going to take the negative 4i times the negative 5i, which is a positive. A negative times a negative is a positive 20i squared. Now, finishing this up, there's nothing I can do here, but I squared is a negative 1. So I end up with a negative 12i. 20 times a negative 1 is a negative 20. And I'm going to put that negative there. Okay. Rather than plus a negative, because this would be plus a negative 20, I'm just going to make it minus 20. So putting it in the form a plus bi, where the a is the real part and the bi comes second, I'm going to go a negative 20 minus 12i. I'll put the real part first. Okay, just so it matches the form a plus bi, where your a is a negative 20 and your b is a negative 12. And then the b has the I with it. Okay, so again, we multiplied them, and when you are multiplying these negatives, you do need to take the negatives out as an I and then multiply, and what's outside and then what's inside, and then reduce. And a lot of times, and again, when you see this I squared, make sure you put a negative 1 when you have that in your answer. That's occurring quite often, you'll notice. Okay, let's look at E. Well, E, looks like we're at the FOIL method. Never goes away, does it? Okay, let's look at our FOIL method. The first times the first. So we'll take 1 times 4, okay, which gives us 4. I'll put it right here. I think I'll have enough room. Then, so first times the first, the outsides, 1 times 3i is 3i. The insides, 2 times 4 is 8i. So I'm using the FOIL, I'm on the OI now. Okay, so I did the first times the first, the outside and the inside. When I combine these, I get 11i. There's my OI in the FOIL. Then I'll take the last times the last. So now I'm going to take 2i times 3i, and I'm going to get a positive 6i squared. Whenever you multiply these common bases, you add the exponents on them. Whenever you see that I squared, okay, we're going to finish it now. You're not, if you stopped here, you would miss it because it does need to be simplified all the way. But here, I squared is a negative 1. So that is a negative 1. Okay, that means a negative 1. So 6 times a negative 1 is a negative 6. So we still have plus. Now you can combine the minus 6 and the 4. So I'm going to do the real part. I'm going to do our real, oh, can't see that very well, sorry. Okay, so I'm going to do the negative 6 and the 4 that don't have the I with them. That's considered the real part. I'm going to do that first. So negative 6 and positive 4 is a negative 2. And then the 11i is by itself, no other i's to combine it with. So there's our negative 2 plus 11i. There's our complex number with our real part and our imaginary part using the FOIL method. So it's not really as difficult. Really, it's just like a variable. It's just that at the end, our I squared by definition is a negative 1. So we put that negative 1 in. Well, let's go ahead and let's practice this here. Let's look at multiplying. Now, in the last chapter, when we were rationalizing the denominator, we introduced a term called the conjugate. Well, the conjugate is where they match and the sign is opposite. And we multiplied by the conjugate so that we didn't end up with a radical in the denominator. So in other words, if I had 2 plus the square root of 3, I multiplied by 2 minus the square root of 3. And the square root of 3's dropped out. And then, of course, I had to do the same thing in the numerator as well. Well, here, these are conjugates, and and let's see what happens to the I. We know what happened to the radical. It dropped out when we multiplied this 2 plus the square root of 3 with this radical inside, this irrational here, so that we could rationalize it. We multiply by the conjugate. Well, let's see what happens here with our 2. I'm going to erase this. Our fraction with our irrational. So again, using our FOIL method, we're going to take the first times the first. 5 times 5 is 25. Okay. Then I'm going to multiply the outside, negative 35i, and we're going to multiply the insides, a positive 35i. Okay. Well, when I combine those, they drop out. The i's are gone. So we don't have that I part anymore, but we're not done with the FOIL, but I do know that the O and I, the i's dropped out here. These dropped out. Let's go ahead and take the last times the last. Positive 7 times a minus 7 is a minus 49 I squared. So I took the last times the last. Well, I squared is a negative 1. So now I'm going to multiply before I subtract these. So I'm going to have 25. This right here, when I multiply, I get a negative 49. 49, and which gives me a positive 49. And some of you may have just been able to put plus 49. 2 negatives here is going to give you a positive 49 when you multiply them together. So my answer comes out to be 74. Whoop. Okay, so we come up with 74, and notice that's it. This comes out to be, you just have the real part. The imaginary part is gone. You just end up with the real, okay, well, positive 74. So again, that's just kind of, how we multiply using our new numbering system, introducing our imaginary number I, remembering that I squared is a negative 1. So that definition allows us to deal with negatives in the radical. It also, remember, I squared is a negative 1. We substitute it in. And kind of an interesting thing is that when you multiply conjugates, you end up with a real number with no imaginary part. And when you multiply these, use the FOIL method. Okay, so that's multiplying. Let's go ahead and look at division. See what we've got here with division. So that seems very small. So I'm going to try to make this so we can see it a little bit better. We know from the last one that we just did that when you multiply conjugates, just like we did if that last term had been a radical, the radicals disappear. When you multiply conjugates, the imaginary part disappears. Well, the same thing with this division. They want you to get rid of the I in the denominator. And so what we're going to do is we're going to multiply by the conjugate. So it's just like, rationalizing. They also want to get rid of, they want to simplify this whole thing so it fits this form. Okay, so that the A part is separate from the B part. And the answer, when we get the answer, you'll see what I mean by that. But again, the denominator, I've got to copy this over. That is way too small. So 1 minus 2i. I'm going to multiply by 1 plus 2i. It looks like a z, but it's not. It's a 2. Oh, maybe I'll round it off just a little bit. So we're going to use our FOIL method twice here. And I don't think they're as bad as the radicals, but oh well. Maybe you guys think they're just as bad. But multiplying, we'll just go ahead and do the numerator. And we're going to use the FOIL method. We're going to take the first times the first. Well, a minus 5 times 1 is a minus 5. And then we're going to have the outside is a negative 10i. The inside is a multiplying those is a positive 9i. Adding them, we get a negative 1i. I'm just going to put a negative I, not a negative 1i. You guys got that. Then we'll take the last times the last. 9i times 2i is a positive 18i squared. I'm going to go ahead and finish this numerator because when you see that I squared, it's a negative 1. So a negative 1 times 18 is a negative 18. Maybe I can put it over here. Negative 5 minus I minus 18. And then combining, we're going to combine the minus 18 and the minus 5. That gives us a minus 23i. And then, oh, excuse me, no I with those, it's just minus 23. And then we're going to have a minus I, which needs to stay alone because there's no other I to combine it with. So I used my FOIL method in the numerator and came down to this right here. Yeah, I do have the light on. Okay. All righty. So now we're going to go ahead and go through the same thing with the denominator. So now I'm going to go underneath here and see what we have. FOIL method. Now we know these are conjugates, so if the i's don't drop out, we've done something wrong. So we'll take 1 times 1 is 1, positive 2i, and a negative 2i. When you multiply the outside and the inside is 0. So then we take the last times the last, and we get a minus 4i squared. Now a minus 4i squared is a negative 1. A negative 4 times a negative 1, when I multiply these, I'm going to get 1 plus 4. Okay, so 1 plus 4, because the I squared is a negative 1, so you multiply these and you get plus 4, which gives you 5. So it's not really rationalizing, but I've gotten rid of my my imaginary number in the denominator because you can see now I can write it as a real part and as an imaginary part. I can put that 5 underneath each of these. So this means the same thing. Okay, so I have a real part and I have an imaginary part. So you can separate it under, which we like to see. And another way you could have done this is you have a negative 23/5. So either you have your real part and imaginary part, or you can, instead of divided by 5, you can write it as times 1/5. Those mean the same thing. So again, because we were able to rewrite this to look like this, then I can divide it into a real part and an imaginary part. And for some of you, when you get into your upper level math, you would be able to graph that with the imaginary part and the real part. Okay, all righty. So questions on that? Well, never mind. If you guys have questions, you're going to have to contact me. So we're going to look at a different one, 5i. All right, so what do we multiply by with this 5i? I need another sheet of paper. Okay, let's look at 7. I just have another piece of paper because I ran out of room. Over 5i. I'd like to get rid of that I, and you have some options. I would just multiply by I. Okay. Multiply by the number I. And the reason is, I know that I times I is I squared, which is a -1. So you can just multiply by the I. So it's a little bit simpler than the last one. Because of that subtraction symbol on the last one, we had to multiply by the conjugate in order to get rid of the I underneath. But with this single one, we just need to multiply by an I. So let's go through that. Notice the parentheses I put around the 7 and the 3i. 7 times I is 7i. 3i times I is 3i squared. 5i squared. Okay, multiplying those, and now we just simplify them. Here we have 7i. This is a -1. So 3 times a -1 is a -3. This right here is a -1. 5 times a -1 is a -5. Okay? So now I'm going to rewrite it. So I'm going to separate these, and I'm going to put 5 underneath both of them. And doing so, I will end up with a -7/5 I. Now I see this negative. It doesn't matter whether it goes with the 7, here, or here, as long as it's there. You can go here, here, or here. Just that minus goes somewhere. And then we have a -3 over a -5 is a positive 3/5. Okay? Most of the time in your math career, we'd always say, well, if you have a common denominator, you can put them under 1. Well, now we're going backwards and we're separating them out. So we have our real part as being 3/5, and our imaginary part, and you could put plus a negative, but I think we'll go ahead and do a -7/5 I. So there we have our answer. 3/5 minus 7/5 I. Okay, terrific. So again, this is division, going through division. The last thing, so okay, again, we added, we subtracted, we multiplied, and then we looked at 2 of the divisions that you need to do, which really, maybe they're not too bad. Now we're going to look at the i's themselves and some of the ideas. What happens if you have I to the 30th? And we're going to reduce our i's. The thing about these is that they repeat. So let's say I have I to the 1st, I to the 2nd, I to the 3rd, I to the 4th, and then we're going to look at I to the 5th. So we're going to look at these before, so you guys can see the pattern that's created. I need a blank sheet of paper so it doesn't confuse you. I want you guys to see this pattern. Kind of cool. So we have I is equal to I. Okay. I squared is a -1 definition. I cubed. Well, I cubed is I squared times I, correct? Because you add the exponents to go from here to here. I know this is a -1, which means that I cubed simplified is a -I. So we have I, then we have a -1, then we have a -I, and now let's look at I to the 4th. I to the 4th is I squared times I squared. I squared is a -1 times a -1. Okay. 2 plus 2 is 4. -1 times a -1 is a +1. So we have I, then a -I, excuse me, we have I, -1, -I, +1, and now let's see about I to the 5th. I want you to see this pattern. I to the 5th is I squared times I squared times I to the 1st. Well, this is -1 times a -1 times I. So you get a +1 times I here, which is just I. And so I to the 6th comes out to be a -1. Okay. I to the 7th comes out to be a -I. I to the 8th comes out to be 1. So we have I, -1, -I, 1. I, -1, -I, 1. So there's a pattern here that we're creating. So when you look at these over here, you've only got 4 options. Your answer is either going to be I reduced, it's going to be a -1, it's going to be a -I, or it's going to be a +1. Your answer is going to be one of those because it just keeps repeating again and again. And this is again why it works with wave theory. It's because it repeats. Okay, this is one of the reasons. It's a rotation. But so let's look at I to the 30th. Which one of these will it be? Well, let's go ahead and let's work with our I squared. If I were to divide this by 2, okay, let me see if I can get that to, I want it to there, blow up a little bit. All right, I to the 30th can be written, divide that by 2, and I get 15. So in other words, I want to know how many I squareds there are in here. So we're going to go ahead and we're always going to be dividing by this 2. So 2 times 15, a power to a power is 30. Okay. Now this is a -1. Okay. We know that if you have an odd power with a negative, it stays negative. If you have an even power to a negative, it becomes a positive. So there's your answer, -1. Okay, I'm not sure if I like it. I'm gonna zoom back out. Okay. All right, let's look at the 49. Now, in order to do this, I need this to be an even. So I am going to make this I to the 48th times I. So I'm going to take out an I here. It's this right here. So whenever you have an odd power, go ahead and subtract 1 from here and put that 1 here. So if I were to come back, these two are equal, those two are equal statements. I to the 48th is equal to I to the 1st. I'm going to move that down here. So just subtract 1. The 1 you take away, put it right here next to it. Divide this by 2. So 48 is going to be, okay, I squared, divide that by 2, and you get 24. And there's the 1 you took out from the 49. So you're trying to make it even so that you can divide it by 2. So if it's odd, just bring one of them and set it over here. Now, -1 to the 24th. Okay. And I squared is a -1. A negative to an even means +1. Times I is 1I. So again, remember our answer was either going to be I, -1, -I, or 1. Those are our only 4 choices in all of these. Otherwise, it just repeats. So here we have a -1, and here we had an I. All right, let's look at 24. 24 is even. If it's even, you don't have to do this step and bring one of them over to the side. So all we do is we divide 24 by 2, and you get 12. 2 times 12 is 24. You rewrote it. I squared is a -1. So this right here, this is even, so it's going to be a +1. And there's your answer. I to the 24th is equal to 1. I to the 49th is equal to I. And I to the 30th is equal to a -1. So we're reducing. Okay, let's try another one. 75. Okay. Here it's odd, so I'm going to take one of them out. I'm going to make it I to the 74 times I. It's equal, because you would add exponents and come back. Now I'm going to rewrite this one using an I squared. So I'm going to have I squared. To get the power, take 74 divided by 2, 37. 2 times 37 gives you 74. We still have that times I. This is a -1. Okay. -1 to an odd power remains negative. We'll just go ahead and put the -1. So -1 times a -1 times a -1 times a negative. You're going to do that 37 times. You're going to get a -1 times I. There's your I right there. -1 times I is a -I. So we ended up with this. Oh. So we ended up with this answer. Okay. All right. Let's try another one. This negative to the 71. Well, this is an odd power. Since this is an odd power, do I keep my negative in doing this entire problem, or would it go? Well, because this is odd, this negative is going to stay. So in doing this problem, it's the same thing as a -I to the 71. You can deal with this, and that negative will be right there. Okay, so you know that negative is going to stay. If this had been 72, the negative would have gone away. And then you would have just dealt with I to the 72. But that's going to remain. So we're going to have, we'll go ahead and keep it there. I to the 70th times I. It was odd, so I subtracted 1 out. You always want this first one to be even. Divide that by 2. I'm leaving that negative outside of this, and I'm going to have 35. So that negative is outside of this. 35 is odd. So that means this is equal to a -1. But you still have this negative, and you still have the I. So you've got this negative. It came from this. Came from this right here. This is a -1 because this is odd. So an odd to a -1 is -1. So you end up with a positive I. There you go, positive I. So you had 2 negatives, which gave it a positive. All right, let's try another one. Our last one, then I'm done. Okay, we have -3 to the 5th. We have to do these separately. But the -3 is to the 5th power. It's in the parentheses. So I know it's going to be negative because that's odd. But you need to ask yourself, what's 3 times 3 times 3 times 3 times 3? So 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. I to the 5th. Okay. So we have we have negative 243 times I to the 5th. Well, what's this equal to? And we're going to take whatever we get here times this. This right here is I to the 4th times I. Okay. I to the 4th we did earlier, but let's go ahead and go through it. This is I squared squared. Okay. Because 2 times 2 is 4. This is a negative 1 squared. So we're just doing this part right here. This is even, so that becomes, that's a positive then. So positive 1 times I, which is I. So we take our I times a negative 243. And we're done. Okay. So, we've introduced a new numbering system. We have opened up a way for you to solve all of our equations, all of our quadratic equations, and we just kind of learned how to work with the I, the number I. We added, subtracted, multiplied, divide, and then we simplified some I's. And you have 4 choices for your answers. Okay, and in order to do that, if it's even, just divide that by 2, and you'll have either negative 1 to an odd, or you're going to have a negative 1 to an even. A negative 1 to an odd is negative, and a negative 1 to an even is a positive 1. And okay, complex numbers. If you have any questions, let me know. Otherwise, I'll open up the homework. All right, good luck.